In this video, we'll continue to look at electricity and we'll be taking a look at resistance, right? So according to the CSEC physics syllabus, these are the requirements that we need to cover under the topic of resistance. So we need to be able to explain the concept of resistance, apply the relationship R equals V over I, explain why it is necessary for an ammeter to have very low resistance, explain why it is necessary for a voltmeter to have very high resistance, and of course solve problem using series and parallel resistance, and in particular using the equations RT equals R1 plus R2 plus R3 for resistors in series, and of course 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 for resistors in parallel. Now let's talk about resistance. Now what is resistance? Now resistance of course is a noun which comes from the verb to resist, right? Now what does it mean to resist? A synonym for resist is oppose. To resist is essentially the same thing as opposing or to oppose something. So if you're resisting something, you're basically opposing it. So when we speak about resistance, we're basically talking about opposition to something. And what is that thing that is being opposed? So since we're talking about electricity, we'll use the correct form of the term. So we'll talk about essentially electrical resistance. Right? So we're talking about electrical resistance. Now, we would have previously met charge, and we'd have also spoken about electric current. And we're able to define an electric current as the rate of flow of charge. So basically, whenever we have an electric circuit and there's a current flowing, it basically means that charge is moving between points within that circuit. Now, whenever charge is flowing in a circuit, the charge doesn't have this free, unobstructed path. So there is some amount of opposition to the flow of that charge. There is some amount of resistance. So when we speak about electrical resistance, we're basically talking about the opposition to the flow of an electric current or to the movement of charge. So electrical resistance is the opposition to the flow of electric charge or currents, right? So once again, we know current is the rate of flow of charge, and electrical resistance is essentially the opposition to the flow of an electric charge or to the flow of an electric current, right? That is essentially what resistance is. Now at this level, we don't need to go into the intricate details of what causes resistance. We just need to know that basically whenever current is flowing in a circuit, their charge is basically being opposed, and this opposition creates electrical resistance. Now, and we also mentioned previously that current will flow to the path of least resistance. What exactly does this mean? If in a circuit there are multiple paths for the current to flow, and one path has a small amount of resistance compared to another which has a larger amount of resistance, then the current will basically, most of the current will actually flow to the path of the least resistance, right? Now one analogy I tend to use, for instance, when it comes to resistance and current, is garbage in a drain. Now if you imagine a drain, whenever the drain is clear and it rains, then the water basically has a clear path to flow. It is not being opposed by anything, right? However, when the drain is full of garbage and it rains, then essentially the water has a much smaller path to flow. So less water flows in the drain because it is basically clogged up with garbage. So essentially in this scenario, the water essentially represents the electric current, and the garbage represents the resistance. So the greater the amount of resistance, the less current flowing in a particular part of the circuit. And the greater the, right, and the smaller the amount of resistance, then the greater the amount of current flowing, right? And of course, we could say the drain essentially is the conductor through which we expect, or the path through which we expect electric current to be flowing. All right, so with that said, let's continue with the objectives of the syllabus. Now, according to the syllabus, basically, we should be able to apply the relationship R is equal to V over I. Now, we define electrical resistance as the as a measure of the opposition to the flow of an electric charge. We previously met Ohm's law, and of course we saw that the equation V equals IR occurred as a consequence of Ohm's law, And of course, from this equation, we can make R the subject, and so we get R is equal to V over I. And so basically what this equation allows is for us to calculate the resistance of a particular, say, component, if we know the potential difference across it, and we also know the current flowing through it as well. So let's say, for instance, we have a conductor where the PD across it is, say, 100 ohms. Sorry, not 100 ohm, but 100 volts. 100 volts rather. And the current flowing is equal to 5 amperes. Then this would mean that the resistance R given by V over I would be equal to 100 volts divided by 5 amperes. And of course, 5 into 100, that gives us 20. Now this unit would be the volt per ampere because we're dividing volts by ampere. But of course, when calculating resistance, we don't often write out volt per ampere. The volt per ampere is equivalent to what is called the ohm, right? So the SI unit of resistance is the ohm. So this is ohm, OHM, and the symbol is the Greek letter omega, right? So I'm sure you've heard the expression alpha and omega, beginning and the end. The omega is the last letter of the Greek alphabet and is used in electricity to represent the unit of resistance, which of course is the ohm. So basically what this is saying is that when you speak about this unit there, then you can say that 1 volt per ampere would be equivalent to 1 ohm, right? And so we can speak about 1 ohm being the resistance of a conductor when through which a current of 1 ampere flows when the PD across it is 1 volt. So I'll repeat that. When we speak about a resistance of 1 ohm, we can think of 1 ohm as a resistance of a conductor through which a current of 1 ampere flows when the PD across it is 1 volt. So in other words then, if we have a conductor, let's say a piece of wire, and we have a potential difference, or we apply a PD of 1 volt across a conductor, and we measure the current flowing through it, which measures 1 ampere, then based on our calculation, it would mean the resistance of that conductor would be 1 ohm. But of course, for a typical conductor, like say this piece of wire, the resistance is likely to be far less than 1 ohm. And so usually in electrical circuits, we often assume that these connecting wires have negligible resistance. And of course, in a subsequent video, we'll do a lot more questions. We will be using these equations to calculate resistance. Where's my class theory? All right, so moving on to the next requirement of the syllabus. The syllabus mentions that we should be able to explain why it is necessary for a voltmeter to have a very high well, not that one first. Explain why it is necessary for an ammeter to have a very low resistance, and of course, right after that, to explain why it is necessary for a voltmeter to have a very high resistance. Now, let's draw a simple circuit on the board. We have a battery, and let's say that battery is driving a current I through some, let's say a lamp. Let's put two lamps connected in series. So we'd have met series circuits before. So we're going to draw 2 lamps connected in series, right? Now, we want to be able to measure the current flowing through this circuit, and in order to do that, we must have an ammeter connected in the circuit. So as we looked at circuit symbols before, and the symbol for an ammeter is a circle with the A in it, and let's say we also want to measure the voltage or the PD across one of these lamps, L1. So we have 2 lamps, L1 and L2, connected in series, and we want to measure the voltage across one of these lamps, say L1. So this is our battery of EMF. Well, let's just call it E, or the battery voltage E. Let me put a value. Let's say it's a 5 volt battery. Right? Just for argument's sake, it's a 5 volt battery. Now we have a current flowing I. And as we mentioned before, in our circuit, we show the direction of conventional current. So even though we know that it is really electrons which are essentially flowing in the circuit, we show the electric current to be the direction that positive charge would actually flow, right? So basically, this battery is driving a current I, and of course, we're measuring the current using the ammeter. The current will pass through these two lamps that are connected in series, and this voltmeter is measuring the voltage across one of those lamps. Now, why do we need an ammeter to have very low resistance? Now, as we defined resistance or electrical resistance is the opposition to the flow of electric charge or to electric current, right? So what this means is that the greater the resistance, the smaller the current that will actually flow in any part of a circuit. So if in a circuit there are multiple parts of different resistances, then the largest current will always flow to the path of least resistance, right? And so basically it means that if we want a lot of current to flow in a particular part of a circuit, we need to make the resistance as small as possible. Of course, this has its disadvantages, but we're not going to get into that, right? So essentially now, when we're measuring a current, we want to know exactly how much current is actually flowing in the circuit. So if there are 5 amperes flowing in the circuit, we want the ammeter to be measuring exactly that 5 amperes. Now, if this ammeter should have, say, a large resistance, it will basically provide a large opposition to the flow of the actual current in the circuit, and only a small current will actually flow in the circuit, or through the ammeter, that is. So if the ammeter has a large resistance, the reading that it will display will not be true or not be reflective of the total or the true current flowing in the circuit. So for this reason, because we want to display the exact current flowing in the circuit, ammeters must have very low resistance. Otherwise, they will not give us a true current which is flowing in the circuit, right? In theory, ammeters, when we speak about an ideal ammeter, we talk about one which has zero resistance. But of course, in practice, ammeters are never ideal. So they never have zero resistance, but they do have low resistance, right? So once again, ideally, an ammeter ought to have zero resistance, but in practice, it has low resistance because we need to be able to measure the entire current or as close to the maximum current flowing in the circuit using the ammeter, right? So that is why ammeters need to have very low resistance. Now, why do voltmeters need to have very high resistance? Now, let's examine this circuit. Now, let's imagine that, for instance, let's put some values here. Now, let's say, for instance, we have a current of 2 amperes flowing in the circuit. And let's say this lamp has a resistance of, say, let's say this is a 1 ohm lamp. This is a 1 ohm lamp, right? This is a resistance of 1 ohm, and this one has a resistance of, say, 1.5 ohms, right? Let's do some calculations. Now, because this current is flowing through both lamps, they're connected in series, then the PD across lamp L1, so let's call this lamp L1, the PD across that, let's call that V1. So V1 would be equal to 2 amperes using IR. This will give us 2 amperes times 1 ohm, which gives us 2 volts, right? Let's look at lamp L2. Lamp L2, let's call it V2, same formula IR. This will be equal to 2 amperes times 1.5 ohms, which gives us 3 volts. So if it's a 5 volt battery driving 2 amperes through this, essentially notice that these 2 voltages, 2 volt plus 3 volts, add to give the battery voltage, as you explained earlier about components connected in series, right? Now, this is what is supposed to be the potential difference across these lamps if the voltmeter is not pulling any current. Now, in theory, we say that a voltmeter is ideal, meaning that it has infinite resistance. Infinite resistance means that the voltmeter will pull absolutely no current. But in practice, voltmeters are not ideal. They do not have infinite resistance, but they have a very large resistance. So even if they are pulling a current, it is very tiny and is not significant enough to cause any change in the potential difference across devices. So these calculations that we made were for the case where the voltmeter was not pulling any current at all. Now, let's imagine a scenario now where the voltmeter is actually pulling a current. Now, let's imagine that this current is flowing is still 2 amperes, but because the voltmeter is going to pull a current, let's say we have 0.2 amperes flowing towards the voltmeter. This would leave 1.8 amperes flowing through these lamps, right? So if the voltmeter is pulling even a small current, let's say roughly 0.2 amperes, it leaves 1.8 amperes to flow to these lamps. If we were to do over these calculations using 1.8 amperes, then this one will be 1.8 amps times 1 ohm, which gives us 1.8 volts. And this one, of course, would be 1.8 amperes times 1.5 ohms, which gives us 2.7 volts, right? So basically, what this would show is that because the voltmeter is now pulling a current, we're not getting the true voltage across these devices, what they're supposed to be. And so for that reason, voltmeters ought to have a very high resistance so they do not pull any current away from the devices in the circuit across which you're connecting the voltmeter to measure the voltage, right? So if the voltmeter is pulling a current, then it basically means that the voltage that we're actually seeing will not be the true value based on the current that is supposed to be pulled by the device, right? And for that reason, voltmeters ought to have very high resistance, so they basically pull no current from the circuit, right? So to sum it up, when we speak about ammeters and voltmeters, ideally we want ammeters to have zero resistance, so they pull all the current flowing in the circuit, and we want voltmeters to have infinite resistance, so they don't pull any current at all. But as I said before, voltmeters and ammeters are never ideal. So ammeters will have a small resistance, so they still pull the bulk of the current, and voltmeters will have a very large resistance, so they only pull a tiny or negligible current from the circuit. All right, so moving on, according to the next objective of the syllabus, we're supposed to be able to solve problems using series and parallel circuits. Of course, before we go into that, let's examine resistors in series and resistors in parallel. Right, so resistors in series. Let's just draw some resistors in series. You don't really need to have a battery. We'll just put a battery. Right, so what we know about resistors in series, we did look at series circuits before, and we mentioned a couple of characteristics of components connected in series. We said that if components are connected in series, the same current flows through all of them, or the current flowing through any point in the circuit is the same. And we also saw that the potential difference across the total PD across the components was equal to sum of the individual PDs across the components. Now, the syllabus doesn't require us to be able to derive these expressions, but it just requires us to be able to use them. So for instance, if we have 3 resistors of resistance R1, R2, R3 connected in series, then their total resistance RT is simply given by R1 plus R2 plus R3. So what this basically means is that when you connect resistors in series, you simply add their resistances. So for instance, suppose R1, let's say R1 is equal to 5 ohms, this is equal to 10 ohms, and this is 12 ohms, then it would mean that the total resistance is equal to 5 ohms plus 10 ohms plus 12 ohms, and that gives us 27 ohms, right? So that would be for those connected in series. So in other words, then basically, when you connect resistors in series, the overall resistance will increase. And oftentimes, this may be the case. we may be designing a circuit and we want to have a certain amount of resistance in the circuit, but that amount of resistance is not available in a single resistor, and therefore if we want a greater amount of resistance than what we have in a single resistor, we generally connect them in series so that their resistances will add, right? So resistors in series. Now let's look at resistors in parallel. So resistors in parallel. So once again, when you looked at parallel circuits before, if there's a current flowing here, then there's going to be a current I1, current I2, current I3, right? And of course, we established that the PD across them will be the same. So the PD is V, right? So again, once again, the syllabus does not require us to be able to derive these expressions, but we'll just use them. Now, if resistors are connected in parallel, as they're indicated here, and by the way, looking at circuits, we should be able to tell how they're connected. But of course, we'll do a lot of questions and get some practice and able to determine how resistors are connected and so on. Now, these resistors are basically connected in parallel, and the expression which gives their total effective resistance is this: 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So if three resistors of resistances R1, R2, R3 are connected in parallel, their total effective resistance RT can be obtained from this formula: 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Now if you look on the right hand side of this equation, these look like three fractions, and of course, you know, I'm sure you remember how to add fractions. You could find their LCM and proceed to add, or we could just go to our calculators. So let's just put some simple values here and find the total effective resistance. So let's say R1 is equal to 2 ohms, R2 is equal to 3 ohms, and R3 is equal to, say, 6 ohms, right? So we have 1 over R1, or 1 over RT rather, equals 1 over 2 plus 1 over 3 plus 1 over 6. We draw a line and we find the LCM of 2, 3, and 6. The LCM of 2, 3, and 6, of course, is 6. So say 2 into 6 goes 3, 3 ones are 3. 3 into 6 goes 2, 2 ones are 2, 6 into 6 goes 1, 1 times 1 is 1. And so we have 1 over RT is equal to 3 plus 2, 5 plus 1, 6. This is 6 over 6, which is equal to 1. Now, that is not the total resistance. If you notice, this is 1 over RT. Then you have to say now that RT would be equal to 1 over 1, which is just 1. But if this had not worked out to be 1, then you'd have seen the difference. Now let me just change one of these values then, so we don't get this to be 1. Let this be, I'm going to make this be, let's make this 4 ohms, right? Let me just change this to 4, so you see exactly what I'm talking about. So this, let's say this is 4. Right, so let's say that is 4. Now, what is the LCM of 2, 3, and 4? Of course, LCM, least common multiple, the smallest number that each of these can divide into, and that number will be 12. So the LCM of 2, 3, and 4 will be 12. Then we say 2 into 12 goes 6, 6 times 1 is 6. 3 into 12 goes 4, 4 times 1 is 4. And then 4 into 12 goes 3, 3 times 1 is 3. And so we have 1 over RT will be equal to 6 plus 4, 10. 10 plus 4 is 13. This is 13 over 12. So this is 1 over RT. So this is the reciprocal of the total effective resistance RT. But what you want to find is RT. So then have to basically flip both sides. And so we get RT will be equal to 12 over 13, which of course is less than 1. So 12 divided by 13 is approximately 0.92 ohms, right? So the total effective resistance of these three resistors connected in parallel would be 0.92 ohms. So what do we notice from based on these calculations? We should be able to observe that basically whenever we connect resistors in series, the total resistance is always greater than the individual resistors in the circuit because of course they're adding the resistances, right? So if you want to increase the resistance, we simply connect them in series. However, we should also notice that when you connect resistors in parallel, as evidenced from this example, the total effective resistance is actually less than even the smallest resistance in the circuit. So in this particular case, we use a 2 ohm resistor as the smallest, and of course, the total effective resistance is 0.92, which of course is less than 2 ohms. So generally, this is always going to be true for resistors connected in parallel. The total effective resistance will always be smaller or less than the value of the smallest resistance. So you can always have an idea of whether or not your calculation is correct. So for instance, if you use 2, 3, and 4, I end up with something like 2.5 as a total effective resistance, then that should tell you something was wrong because you can't have the total effective resistance being greater than the least value of the resistances connected in parallel, right? So we are able to basically do simple examples of resistors in series, now resistors in parallel. Now let's examine the equation for resistors in parallel a little bit further, right? Now let's examine the case where it is just 2 resistors in parallel. 2 resistors in parallel and not 3. So let's say it's just, let me just rewrite this. So if it is 2 resistors in parallel, R1, R2, then essentially the formula becomes 1 over RT equals 1 over R1 plus 1 over R2. Now let's treat this as 2 fractions. Whenever we have fractions, to find a common denominator, the easiest way to do that is to actually multiply the 2 denominators. So if we have say a fraction like 1 over 3 plus 1 over 4, then the easiest way to find a common denominator, doesn't have to be the LCM, is to actually multiply the 2 denominators. So 3, 4 is 12. So the common denominator, which of course will be 12. The same thing is we're applying here. So this is basically R1 times R2. This into this will leave R2 because the R1s will cancel. And so R2 times 1 is R2. Then this into this leaves R1 because the R2s will cancel. R1 times 1 is just R1. And so we have 1 over RT is equal to R1 plus R2 divided by R1, R2. But as before, what we're interested in finding is not 1 over RT, but RT. And so therefore, if we flip both sides, then what we get is this. RT is equal to R1 times R2 over R1 plus R2. Now, what is the significance of this? The significance of this is this. If it's just 2 resistors connected in parallel, their total effective resistance is simply their product divided by their sum. So if it's just 2, we don't have to write out 1 over R1 plus 1 over R2, find LCM, and then find the total resistance. No. If it's just 2 resistors connected in parallel, then the total effective resistance is simply their product divided by their sum. So in other words then, if we have this, if this is say a 5 ohm resistor, and this is say a 4 ohm resistor, then the total effective resistance, RT, is simply equal to 4 times 5 divided by 4 plus 5. So this gives us 20 divided by 9, which is about 2.11 or 2.20 divided, no, not 2.11, but 20 divided by 9. It's about 2.22, so 2.22 ohms, so let's just 2.22 ohms, right? So once again, if it's just 2 resistors connected in parallel, we don't have to go through 1 over R1 plus 1 over R2 and find LCM. We can simply say the total effective resistance is the product of the 2 divided by the sum of the 2. But however, this only applies if it's 2 resistors connected in parallel, right? Now, what about the case of identical resistors connected in parallel? Suppose we have identical resistors in parallel. So let's say, for instance, we have 3 resistors, each of resistance R. Right? Using the same formula that we did before, we can say that 1 over RT is equal to 1 over R plus 1 over R plus 1 over R. And the denominators in this case are the same. So because the denominators are the same, we can just proceed to adding the numerators. So 1 plus 1 plus 1, that gives us 3. And so we have 1 over RT would be equal to 3 over R. Same denominator. So once again, we just add the numerators. Let me just put in this intermediate step. So if we were to write down R, then it says 1 plus 1 plus 1. And so 1 over RT will be equal to 3 over R. And we then flip both sides because what we're really interested in finding is RT. So this tells us that RT is equal to R over 3. And of course, it's not a coincidence that we end up dividing by 3 because that was the number of resistors, number of identical resistors in parallel, right? So what does this generally show? That if we have n identical resistors, each of resistance R in parallel, so we say for n identical resistors, each of resistance R in parallel, we can say that RT, the total effective resistance, is simply equal to the value of one resistor divided by the number of resistors, right? So this applies, of course, only if they're in parallel and if they are identical, right? So for instance, if we have, say, 5 100 ohm resistors connected in parallel, then the total effective resistance would be equal to 100 ohms divided by 5, and that will give us 20 ohms, right? So we looked at resistors in series and parallel, and we also look at simpler ways of dealing with small amounts of resistors in parallel, like the 2 resistors in parallel. That is just the product of their resistance divided by their sum. And we also look at the case where these resistors in parallel are identical. So once again, if we have n identical resistors, each of resistance R connected in parallel, the total effective resistance RT is simply equal to the value of one resistor divided by the number of resistors.